All right, everyone, welcome to lesson 31 for the semester. So just a reminder, we have our exam 3 coming up this Monday. So that's going to cover all of the lessons on power series and then parametric equations up until and including today's lesson right here. So then that'll be it. So there's going to be 2 more lessons after the exam. So there's going to be polar coordinates, lessons 32 and 33. Those will not be on exam 3, although they will be on the final exam. We're going to have a review for this in class on Friday, and then also the teaching center is going to do a review on Friday evening as well. So I'll post the Zoom link to that later. All right. So let's go ahead and get started with our last lesson here, or our last lesson before this exam. So last time we learned about parametric equations, which is a different way of expressing curves. We have quite a lot more freedom with parametric equations, as we saw, especially at the end. So now what we're going to do today is we're going to learn how to do calculus with parametric equations. So what we're going to do today is we're going to kind of speed run through calculus 1. So we're going to start by doing, well, we're not really even going to do any limits. We're just going to do derivatives, and then I'll talk about how to do integrals with parametric equations here. All right, limits, I guess I'll just say a word about limits. So if you want to do the limit as t goes to 0 of a parametric curve, how should I write this? So you have some parametric curve, you want to see the limit as t goes to, well, really any number. Then that's just going to be the limit as t goes to a of the first function, and then the limit as t goes to b of our second function right here. So limits work exactly the way you would expect right here. All right, now so since limits work exactly the same way you'd expect, derivatives do as well. So since x and y depend on a third variable t, then it stands to reason that we could find the derivative of x with respect to t and the derivative of y with respect to t. Now, I want to emphasize something here. I want to say that this is not equal to dy dx. So if we have y as a function of x, we could do the x derivative of that, and that's one thing. But this is going to be different from dx dt and dy dt. So let me explain the difference between these. So dx dt, if we just do the x derivative of this function right here, and same with dy dt with this function, what this represents is how fast we are moving along the curve in the either x or y direction here. So for example, if dx dt is 2, then we're heading to the right as t gets bigger. We're heading 2 to the right for every 1 t value we go through. And if dy dt was, say, like -1, then we would be moving downwards 1 unit for every t that we go here. In terms of physics, so remember I gave this kind of physics interpretation last time where x and y were the x and y positions of a particle. In terms of physics, dx dt and dy dt represent velocities in the x or y directions. I know you guys had a physics test last night. Sorry if I'm triggering anybody. But anyways, yeah, so if you want to think about this in the physics way, these are the x and y velocities right here. Kind of like related rates in Calc 1. Yes, it actually is similar to that. That's right. Yeah, so this is kind of similar to related rates in Calculus 1. All right, now dy dx means the same thing that it always has. Dy dx is the slope of the tangent line. So it's going to mean that, or it's the rate of change of y with respect to x. So dy dx means these, but then dx dt and dy dt mean these interpretations right here. All right, now there actually is a relationship between these, even though they're not equal, there is a relationship. If you want to find dy dx, but you just have parametric equations for x and y, then we can write them like this. Dy dx is dy dt divided by dx dt. And if you kind of think about derivatives in Leibniz notation here as fractions, you can almost imagine that I just multiplied the top and bottom of this by 1 over dt. That's kind of why this is going to be valid here. So this is going to be our way. If we ever want to get dy dx, like say maybe we want to find a tangent line. So if we want to find a tangent line, we need dy dx. Then the way we would get it with parametric equation is by doing dy dt divided by dx dt right here. What's the word after physics? Velocities in the x and y directions. All right, so let's go ahead and take a look at an example of us using this information. So we're going to find the equation of the tangent line to the curve x equals t cubed minus 4t, and then y equals t squared at the point 0, 4. Okay, now I'm going to give you a little bit of a spoiler here. Something interesting is going to happen with this. It's not just going to be a standard tangent line problem like with Calc 1. Okay, well, in order to get a tangent line, we need to know at the point at which we're going, or at which we're finding the tangent lines. We have 0, 4 here. And then we also need to know the slope of the tangent line, which is dy dx. So we need to figure out what dy dx is here. So dy dx is dy dt divided by dx dt. So dy dt, let's see. So the t derivative of t squared is going to be 2t. And then the t derivative of x will be 3t squared minus 4. Okay, so this is our formula for dy dx in terms of t. Now, that begs the question, which t value do I plug in for my dy dx? Well, that means I need to see which t value makes my x be 0 and my y be 4. So which t value makes x equals 0, y equals 4. All right, well, let's figure it out. So if y is equal to 4, another way of saying y is going to be t squared. So this gives me two different t values, t equals plus or minus 2. So it could potentially be either of these, but let's see if these satisfy the x equation, because it needs to satisfy both equations for it to be the appropriate t value. So let's set x equal to 0, because we want our x coordinate to be 0 here. So we have x is t cubed minus 4t is 0. All right, well, I guess we could factor a t out of this. And then we can factor this. And it turns out that in this case, t could be 0 or plus or minus 2 right here. So it seems like both positive and negative 2 make both x and y be the values that they need to be. So it turns out that there are two different t values that work. Now, what does that mean here? What does it mean if there are two different t values that make our curve pass through this point right here? It means this curve is going to intersect itself. So I don't know exactly what the graph of this looks like, but it's going to look something like this. Like we can imagine this is the point 0, 4, and we're passing through it at two different times. So we go through it the first time like that, and then we go through it at a later time like this. And as you can see here, there are going to be two different tangent lines depending on which way we're going through this point. So our answer to this question, it's not find the equation of the tangent line, it's find the equations of the tangent lines to the curve. So that's really what we're doing here. So we have two different t values. All right, well, let's figure out what our dy dx is for, say, t equals 2. Let's do that one first. So we have dy dx is 2t over 3t squared minus 4. So this is going to be 4 over, let's see, 2 squared is 4 times 3 is 12 minus 4 is 8. We have 1/2. So our first tangent line is going to be y minus 4 is equal to 1/2 times x minus 0. Because remember, it still has to go through the point 0, 4 right here. So we still have that point, it's just the slope is going to be 1/2. Then we have t equals -2. Let's see what tangent line this produces. So we have 2t over 3t squared minus 4. So this is going to be -4. And since I'm squaring the 2, this is still going to be a +4. So we have 12 minus 4 is 8 again. So we end up with -1/2. So this tangent line will be y minus 4 is equal to -1/2 x minus 0. So it turns out that we actually have multiple tangent lines because we're going through the same point 2 different times in 2 different ways right here. So that's why we have 2 different tangent lines. You don't have to put it back in parametric form. They didn't really ask us to do that. So yeah, I guess we don't need to do that here. We could put this in parametric form by making, x equals t, for example, and then y could be 1/2 t plus 4 or something. So if you want to put it back in parametric, you're welcome to, but they didn't ask us to do that here. How come we didn't do this with t equals 0? Because t equals 0 makes x be the right number, but it doesn't make y be the right number. Because if I plug 0 in for t squared, I get 0. But remember that I wanted y to be 4 right here. Now, if I got t equals 0 for this one as well, then we would have included that and it would have intersected itself 3 times. So yeah, but we didn't include it because we don't have it right here. All right, so why don't you guys give this a shot here? And one thing is, it's not always going to have multiple tangent lines. It's just that if it goes through the same point multiple times, it's likely to. All right, so practice 1. Find the equation, or I guess I'll put a parentheses s just to leave open the option we could have multiple, of the tangent lines, and again, I'll put parentheses s, to the curve x equals 3 minus 2t squared, y equals 6 plus 4t cubed. Oh, actually, wait a minute. This one definitely doesn't have multiples because we gave a specific t value at t equals 1. So since we're doing this at a particular time going along the path, we're definitely only going to have 1. All right, so go ahead and find the tangent line here. What was the very beginning with the limits? It's if you want to take the limit along a parametric curve, you simply do the limit of the x coordinate and the y coordinate separately. That's all that's going on there. Oh, what is the b in the very beginning with the limits? Oh, sorry, this was an a. I don't know why I wrote b for that. Yeah, that was an a. All right. Once we find the slope, how can we find the equation if we're not giving a point on the graph? We could find the point on the graph by substituting in t equals 1 into these equations here. And that will give you your x and y. One minus 10 is 3 times x minus 1. Yeah, we'll see in a minute. dy dx gives you the slope of the tangent line. Yep, that's what dy dx is. That's what the derivative means. All right, let's take a look at this here. So first of all, let's compute what dy dx is. We need to know the slope of our tangent line. So we have dy dt divided by dx dt. So dy dt, let's see, that's just going to be 12t squared. And then dx dt looks like that's going to be negative 4t. All right, now let's plug in t equals 1 because that's where we wanted to find the tangent line. So we're going to end up getting 12 over negative 4. It'll be negative 3. So this will be our dy dx here. All right, now we need to know what point this is occurring at in order to use the point slope formula for our tangent line. So we plug t equals 1 into here. So at t equals 1, we have that x is 3 minus 2, which is 1. And we have y is 6 plus 4, which is 10. So in summary, this means that our tangent line has the equation y minus 10 is negative 3 times x minus 1, just as you guys predicted. There we go. There's going to be our tangent line right there. All right, now in calculus, we learned how to compute the first derivative, dy dx. We also learned how to compute the second derivative, d squared y dx squared. And you may remember that that represents concavity, or whether we're bending up in the form of a smiley face or down in the form of a frowny face if we're negative. So it turns out that we can compute the second derivative as well as the first derivative. Oh, Canvas wants parametric. Let's see here. So since we have the point 1, x might be t plus 1, and then y might be negative 3t plus 10. Is that an option? Did they give that as an option? Okay. Yeah, I guess they wanted the parametric for this one. I should change that though, because I don't think I said that. No, I just said find the equation. I guess it could be either way. All right, anyways, so what we're going to do now is we're going to compute the, oh, can I explain how I got that? Yeah, sure. So the formula that we have for lines is x always just has a t there, unless it's a vertical line. X is going to be t plus the x value that we go through. And we're going through the x value of 1. So that's where I get t plus 1 for x. And then y has the slope times t, so negative 3 times t, and then we add in the y value that we go through here, plus 10. Yeah, I got that from the formulas from last time. That's where I got that. All right, so let's go ahead and figure out what our second derivative is. Now buckle up, because this one's going to be a bit more difficult to get than the first derivative. So our goal is to find a formula for d squared y dx squared. Okay, so this will take a second to get the formula, and then we'll go ahead and use this on an example here. So what is the second derivative? The second derivative is the derivative of the first derivative. So this will be d dx of dy dx. All right, now the good news is we already know how to write dy dx in terms of parametric equations. It's dy dt over dx dt, right? But the bad news is that these are usually functions of t, not functions of x. So how will we change this so we're doing a t derivative? Well, if you ever want to do df, this is kind of an aside. If you ever want to do df dx, where f is anything, any function you want, this is going to be df dt times dt dx right here. So this is exactly what we're going to do. Only our f right here is going to be this right here. So we're going to have this. We're going to do the t derivative of it instead. So we have d dt of dy dt over dx dt. And then we're multiplying by dt dx. Now, multiplying by dt dx, we usually don't have t as a function of x. So this one's a little bit weird. So what we could do is we could just put it on the bottom and make it look a little bit better. So we have the derivative of this fraction. And then we can move this to the bottom by taking the reciprocal. So what we have so far is we're going to do the t derivative of this. And then whatever we get for that, we're going to divide by dx dt right here. All right, now we're doing the t derivative of a division or a quotient here. So that implies that we're going to need to do the quotient rule right here. All right, so let's go ahead and do the quotient rule for this. So I'm going to, well, I have my dx dt down here. And then I'm going to, actually, let me not write it. Let me just do the quotient rule for this and I'll divide by dx dt. So I square the bottom. I bring the original bottom up here. And then I do the derivative of the top. Now the t derivative of this will be the second derivative of y, like that, right here. Then I'm going to subtract, and then now I do the derivative of the bottom part, and then I leave the top alone, so I leave dy dt alone. And then remember, all of this will be divided by that dx dt that we got earlier. But we're already dividing by two of those. So it turns out that our final formula here is going to be dx dt, d squared y dt squared. And then we have it the other way around, where we do the second derivative for x, only the first derivative for y. And then, unlike an ordinary quotient rule, rather than dividing by something squared, we're going to divide by something cubed. So there we go. And now an easier way of writing this is to use Newton's notation for derivatives. So we would have x prime y double prime minus x double prime y prime over x prime cubed. That's a bit easier to write right here. Is that df dt on the top right? Yeah, so this is d anything dx is d anything dt times dt dx. And I used this fact right here. Only instead of an f, I just had this fraction right here. So this will not be on a formula sheet, but the way you remember this is just, it's a quotient rule, but you cube the bottom instead of square the bottom here. So this is like an almost quotient rule. Although do remember that you will get the power series on the equation sheet, but you won't get this though. All right, so let's see here. Let's go ahead and actually use this on something here. So let's use this on practice 1 at t equals 1. Let's find d squared y dx squared right here. All right, so let's see. What was our parametric equation for example 1? or sorry, practice 1. Well, it was x is, where do we do that? Yeah, here it is. X is 3 minus 2t squared. Y is 6 plus 4t cubed. And we're doing this at t equals 1 here. This isn't on our test next Monday, right? No, this is on our test. Anything today is going to be on our exam. And then this is the last lesson that's going to be on there. So this will be on the test. All right, so let's go ahead and use this formula here. So it's x prime y double prime minus x double prime y prime over x prime cubed. All right, well, let's figure out what x prime y prime and the second derivatives are. That'll help us. X prime is negative 4t, so x double prime is negative 4. Y prime is 12t squared, so y double prime is 24t right here. All right, so we go ahead and then we plug in t equals 1 into here. So then we have x prime is negative 4 and x double prime is negative 4. Y prime is 12 and y double prime is 24. All right, and then we just plug all these in here. So we have negative 4 times 24 minus negative 4, and then y prime was 12. And then on the bottom, we have x prime cubed, so that's negative 4 cubed. All right, this is negative 96. This is going to be positive 48. And then this is going to be negative 64. So we have negative 48 over negative 64. And this is going to simplify, I think, to 3 over 4. So there's going to be our derivative here. Like I said, this looks kind of intimidating, and you don't need to know how to derive this. You don't need to go through the proof right here. Like I said, remember, it's almost the quotient rule with x prime over y prime. We have the exact quotient rule up here, and then the only difference is we're cubing the bottom instead of squaring it. All right. So that's enough about derivatives. Now let's move on to integrals here. But before we do that, I want to talk about one more thing with derivatives here. And this has a little bit of physics in it as well. So I want to talk about something called the speed. So you may remember that the speed is sort of the absolute value of the velocity. Another way of thinking about it is the speed is the square root of the x velocity squared plus the y velocity squared. So this is our definition of speed. And remember, the difference between speed and velocity is speed is how fast our distance is changing, and it's always going to be positive. And then velocity is how fast our displacement is changing, and it could be negative as well. So this is always greater than or equal to 0. Okay, now what we want to do, so there's speed. What we want to do is we want to compute how long a parametric curve is. So for example, let's say we draw some kind of squiggly like this. And we start here and then we end here. We may be interested in wanting to know how long this path is going to be right here. So that's what we're going to try to figure out right now. All right. So let's see here. How are we going to get speed? Well, here's another physics fact. Distance is equal to speed times time right here. So let's say we want to figure out how far we went over a tiny little distance, or sorry, over a tiny little time. Let's say we want to figure out how long this little chunk is. Then our distance, which I'm going to call distance S, because we're going to be using D's for differentials. So distance is going to be S. So this is saying that ds is going to be the speed. So we have root dx dt squared plus dy dt squared, and then times a little bit of time, dt right here. So if we want to go a tiny little distance, then we could figure out a formula for that right here. It's going to be the speed times the time we go, and this is a tiny amount of time. Now, kind of like what we did earlier in the semester, if we want to figure out the total amount of something, what we do is we add together all of the tiny little amounts together. And when we make those tinier and tinier, we have more and more of them, then we're going to end up getting an integral. So that's where integration is going to come from here. So the total distance is where we're going to add up or integrate over ds right here. But rather than doing that, we want something that we can actually do with t's, because we have our function in terms of t. So in order to get the total distance, which is also called the arc length, we're going to do the integral of the square root of x prime squared plus y prime squared dt right here. All right, so this is going to be our arc length integral, and this is between time t equals a, so that could be like our starting time, and then we could have our ending time at t equals b here. All right, another way of imagining this is we could, so here's kind of a picture for you. We can imagine that we're breaking this curved path into tiny little straight paths. So we might have a straight path here, and it's not exactly straight because it's curved, but it's a close enough approximation. And we could end up making a little triangle right here. Now, if I zoom in, if I enhance this triangle right here, what am I going to get? I'm going to have the curve, which will be kind of bent, and then I'm going to have my triangle here. Now, these are approximately the same length, and this is going to be dy, this will be dx, and then that will be ds right there. All right, so if we use the Pythagorean theorem here, then we're going to end up with dx squared plus dy squared is ds squared. Now, what we could do is we could divide everything by dt squared. And then we could take a square root. And this is where the speed formula comes from. So ds dt, the speed, is going to be the square root of dx dt squared plus dy dt squared. That's where the speed formula comes from. And then we use the speed formula to get our integral right here. So this is an approximation, not an exact answer. It's an approximation if we have only finitely many of these. But as we send the limit of the number of these to infinity, then we get an exact answer. And that's going to be our integral here. So the integral is going to be exact right here. But the little building blocks that we use on our way to the integral, those are approximations. All right, so let's go ahead and use this to try to compute the length of a curve here. All right, so this is going to be an interesting problem here. And this definitely isn't the way they originally did this, but this is a way you can do this. Example 3. Prove that the circumference of a circle of radius r is 2 pi r. So this is a fact that we've kind of taken for granted since whatever grade we learned this in. I don't remember what grade we learned this in, but yeah, this is kind of something that we take for granted. But how do we know for sure this is true? Well, this is actually going to be a proof of it. What we're going to do is we're going to draw a circle of radius r. So that's going to be this, right? And we're going to make parametric equations for this circle right here. So do you guys remember from last class, what are parametric equations for a circle centered at the origin with radius r? What's my x going to be? Yeah, it's going to be r cosine of t. That's right. And then y, naturally, will be r sine of t. And this r is just some fixed constant based on whatever the radius is here. All right, so what we're going to do now is we're going to take this and put it in to our equation here. So we want to figure out the arc length of a circle. So we're going to start at t equals 0 and go all the way around the circle to 2 pi. So our integral will go from 0 to 2 pi, and we have the square root of x prime squared plus y prime squared dt right here. All right, well, let's see what x and y prime are. X prime is negative r sine of t, and y prime will be r cosine of t. Okay. So we have x prime and we square it, so the negative goes away. And then we have r squared sine squared of t. And then we have y prime squared of t, which is going to be r squared cosine squared of t. Okay, now is there any way we can simplify this? Because I don't want to integrate this the way it looks right now. It looks a little nasty, but is there something nice we can do right here? Yeah, so we can use the Pythagorean theorem right here. That's right. So if we factor out the r squared, we end up with a sine squared plus cosine squared. And conveniently, that's just a fancy way of writing 1. So this is 0 to 2 pi. We have the square root of r squared dt. But the square root of r squared will just be positive r because we're assuming our radius is positive. All right. So then all we've reduced this integral to doing is just doing the integral of a constant dt. So as we all know, the integral of a constant is just the constant times the variable. We go from 0 to 2 pi. We can plug 2 pi in for t, and we get 2 pi r. And then we would plug in 0 for t, and we get, well, 0. And lo and behold, we've arrived at our answer. The arc length of a circle, if we go all the way around, is going to be 2 pi times its radius here. So that was a proof of this formula right here. The circumference is going to be 2 pi r. Why do you integrate from 0 to 2 pi? Because we want to go all the way around the circle. So t represents the angle here. We start at an angle of 0, and then we spin our angle all the way around until we hit 2 pi here. So we are taking for granted that we know that a circle has 2 pi radians in it. So I guess we are assuming that. But assuming that, we can then prove that this is the circumference of a circle. Now, I emphasize this is not the way that this was originally done. This is known for thousands of years, long before calculus was invented. This is just one way of doing it. All right, and then let's do one final exercise here, and then that'll be it for today here. And then we'll just do some review next time. So practice 2. If a particle has position function xy is 1 plus t squared and 1 minus t cubed, find the distance the particle travels from t equals 0 to t equals 1. So see how far it travels in its first second, right there. All right. Can we see the original way of doing it? To be honest with you, I don't know the original way that they proved that the circumference of a circle is 2 pi r. I honestly don't know a lot about math history. It's probably in Euclid's Elements somewhere. Well, I think they knew that before Euclid, though. Is the position function the original function? Yes. So this is going to be our x of t right here, and this is our y. So we need to know what x prime and y prime are first before we do anything. would a math class be a math or would a math history class be a math class or a history class? It's actually a little bit of both. So to get an appreciation for math history, you want to actually work through the math that they're doing. We actually offer a math history course in the math department here. So I guess technically it's a math class, but it's really kind of both. I should probably take that class because I don't know anything about math history, to be honest with you. I know Newton invented calculus. I know that. Well, or Leibniz. That's contentious. A Maury show. Oh my God. You are not the father. Oh, that's good. Is it position, velocity, acceleration? Yes. So if you take the derivative of position, you get velocity. And if you take the derivative of velocity, you get acceleration. I guess I should say the derivative of displacement. Yeah, that's right. You can assume that because t is positive. So yeah. Is there a discussion quiz tomorrow or nah? Well, there you need to attend it to get points, but there's not an actual quiz. All right, we'll see what the answer is in a little bit, maybe like a minute or so. Could be another one where it doesn't include the right answer. I could have made a mistake when I wrote it. It's not impossible. When will I post Monday's lesson? I'll post that later today. Sorry, I've fallen behind on that. Also, you guys should be having new homework soon. There's been an issue where like Chronos was like broken for a few days. I think that's fixed now. All right, let's go ahead and see how we would do this here. So we want to find the distance the particle travels. All right, so we know that the distance s is going to be the integral from 0 to 1, so between the two different time values here, of the square root of x prime squared plus y prime squared dt. All right, well, we know that x is 1 plus t squared, y is 1 minus t cubed. So let's get x prime and y prime. x prime will be 2t, and y prime will be negative 3t squared. Okay, so let's go ahead and substitute the squares of these into here. So we have the square root of x prime squared, which will be 4t squared. And then we add y prime squared, which will be 9t to the 4th. All right, so we just need to do this integral right here. So I noticed that I could factor a t squared out of this. And if I move a t squared out of the square root, it'll become absolute value of t, but t is already positive. So we can simplify it to be this right here. Okay, so now we have this integral. Now, what method do you guys think I should do to do this integral? So there's a little bit of early final review here. How do we do this integral? Yeah, we're going to do some u sub. That's right. All right, so u will be the stuff under the square root. So 4 plus 9t squared, and du will be 18t dt. But we don't really have a spare 18 hanging around here, so I'm going to divide by that. All right, so now let's go ahead and change our integral over. So we have 1/18 now, and then we're going to have the square root of u du, and then our bounds will be different. So if I plug 0 in for t, so I do that, I have 4 plus 0 is 4. So my bottom bound now is 4. And if I plug 1 into here, I have 4 plus 9 is going to be 13. So now my integral is going from 4 to 13 of root u. All right, well, this is just a power rule now. So I raise this to be u to the 3/2, and then I divide by 3/2, which is multiplying by 2/3. This goes from 4 to 13 right here. All right, 2/3 times 1/18 is 1/27. And then we have 13 to the 3/2. And then we subtract and we have 4 to the 3/2. But 4 to the 3/2 is another way of saying 8. So we have 13 to the 3/2 minus 8/27. So we have kind of a bizarre number here. But that ends up being our arc length for this one. So hopefully that served as a little bit of a mini integration review here. When we have a polynomial that's 1 degree higher on the inside of a root than something on the outside, u sub is usually the way to go here. All right, well, that's about it for today. And that's about it for the material on the upcoming exam here. So on Friday, we will do some review. You guys can bring any questions you want. You can bring those in and I can help you out with those. Don't forget that there are some old exams and a practice exam on Canvas. So don't forget to use those to study right here. Will the upcoming homework be due Friday or Monday? Definitely not that soon. Maybe one of them will be due Monday. Definitely none due Friday though. All right, that's it for today. So I will see you on Friday.